Hey everyone, in this related rates video, we're going to do an example from chemistry working with Boyle's law. Boyle's law states that when a gas is compressed at a constant temperature, the pressure P and the volume V satisfy the equation or the relationship that the product of the pressure and the volume gives us some constant number C. We're told at a certain instant in time, the pressure is decreasing at a rate of 15 kilopascals per minute. The volume is 1,000 cubic centimeters, and the pressure is 200 kilopascals. With this information, we want to figure out how much is the volume changing by at this moment of time, or what is the rate of change of the volume at this moment. All right, so reading the problem over again, and at the very end, we can kind of find what we are looking for. What we don't know, which we are trying to figure out, or what we want to know, is how much is the volume changing by, or what is the rate of change of the volume. So we're working with some derivative of the volume. What kind of derivative are we going to be working with? What are we taking the derivative with respect to? Usually we can look at the units involved in some of the other quantities to figure that out. And the only other kind of rate we are given has a unit of time in the denominator. So that's our indicator. We're going to eventually differentiate everything with respect to time. So what we want to know about this situation is the rate of change of the volume with respect to time. So now let's identify what we do know about this situation that'll help us find that particular rate. All right, so there's quite a few things we're actually told that we now know about this situation. First off, we're told that the product of pressure and volume is always equal to some constant. That's what Boyle's law tells us. And we're also told at a particular moment in time, the pressure is decreasing at a rate of 15 kilopascals. So that's the rate of change of the pressure with respect to time. And so that quantity is 15 kilopascals, or 15. But since we are decreasing the pressure, the derivative needs to be negative, and our value for the derivative needs to reflect that. So if we had dp dt as positive 15, it would probably give us the incorrect answer. All right, so is there anything else we know? We got dp dt. Let's see, we're told the volume is at 1,000 cubic centimeters. So V is equal to 1,000, and we're also told the pressure at our moment of interest is 200 kilopascals. You might look and notice in our equation, we aren't given that constant C. Since we know the pressure and volume, we can multiply those together to find that constant C. But once we get a bit deeper in this problem, we'll see that we actually never needed to know that constant C anyways. Also, sometimes it's nice to draw a picture to help you organize your information for the situation, but here, since that equation that relates our quantities together is already given to us, I don't think we need a picture. I think we are ready to go. We are ready to differentiate this relationship between our quantities to find an equation that relates the rates of these quantities together. All right, so I've got it set up so that we are ready to differentiate Boyle's law with respect to time. And so remember, this is going to be some implicit differentiation and require use of the chain rule as some of our other derivative rules. And so we have to kind of think of P and V, as well as C, even though it's constant, as a function of time. So if we want to differentiate the left-hand side, then we have a product of two functions of time. So we're going to have to use our chain rule as well as our product rule to help us find the derivative of the left-hand side. So remember, the product rule says you have to take the derivative of the first function, multiply it by the second, and then add to that the derivative of the second function multiplied by the first. And here our derivatives are going to be with respect to time. They're going to give us those quantities like dp dt and dv dt. So if we use the product rule to get started with this left-hand side, we're going to get the derivative of the first factor times the second factor. That's the first half of our product rule. And we have to add to that the first factor, or the first function, times the derivative of the second. So differentiating the left-hand side of our equation implicitly with respect to time gives us dp dt times v plus p times dv dt is going to be equal to the derivative of c with respect to time. And we don't actually want to call that dc dt because we know c is a constant, which means it doesn't actually depend on time at all. And so it's not going to change as time changes, so its rate of change is 0. Or you can just remember, the derivative of any constant is always 0. All right, so now in some of our other videos, we were at a point like this. We would plug in all the values we were given and then solve for the quantity we want. I'm just going to do it a little bit differently in this video to mix things up. I'm going to solve this symbolically for the quantity we were searching for, dV dt, and then at the very end, I'll plug in all the values we know. So if we want to solve or isolate dV dt, we have two terms on the left-hand side. We're going to start by getting rid of that first term, subtract it away from each side of our equation. So if I subtract dP dt times v from each side of our equation, this is what we end up with. We get that first term on the left-hand side, p times dV dt is going to be equal to negative dP dt times v. And now to isolate dV dt, we just divide both sides by p. So dV dt, the rate of change of the volume, is going to be equal to negative dP dt times v over p. Well, now we have the relationship between our rates of interest, and we have it solved for the rate we are trying to find. What we want to know, the rate of change of the volume with respect to time. It's just -1 times the rate of change of pressure with respect to time times the ratio of the volume to the pressure. And so let's go ahead and plug these values in and see what we get. So we get dV dt is equal to negative dP dt is going to be -1 times -15. So these double negatives will cancel out. In our next step, we have to multiply that by the ratio of volume to pressure. That's 1,000 over 200. And so now those two negatives cancel out. Let's see, that's the same as 5. 5 times 15 is 75. And so now we know the rate of change of the volume with respect to time is 75. But what are our units? Well, it's going to be the units of the volume. If we look back at the original problem, we can find them. They were cubic centimeters. And then the unit in the denominator is just going to be the unit of time. And again, if we look back in the original problem statement, we'll find the unit of time was minutes. So the original question was asking, how is the volume changing at this moment of time? So at that moment in time, the volume was increasing at a rate of about 75 cubic centimeters per minute.